everyone. We are Team 3 and we are called the Purgers. My name is Tingshi Chen.
I'm Todd Lattimore.
I'm Justin Martin.
I'm Roman Piro.
And I'm Audrey Tan.
And today we'd like to share our Cumene Project with you guys. So let me briefly go over some background information. The company, Knit Lion Chemical, has a total of 3 locations across the United States, which are Philadelphia, Pennsylvania, University Park, Pennsylvania, and Houston, Texas. We, as the research and development team, are located in University Park, Pennsylvania. The team is responsible for the process development and design of the Cumene plant that will be located in Houston, Texas. This plant will operate 24/7 for 350 days with a scheduled downtime of 15 days. So our goal is to design a chemical plant that produces 374 million pounds per year of 99.98% cumene. The main reaction is reacting benzene with propylene as well as the catalyst to produce cumene, as shown on this slide. However, this main reaction is accompanied by multiple side reactions, such as all these that are shown on the slide. Therefore, in order to achieve our desired purity, we will need a series of distillation columns. Now, let's take a look at our plant design. We will be having a total of 2 types of reactors and 6 distillation columns. This picture shown on the screen represents the schematic of our proposed plant. The benzene will be introduced into our first separator, where the toluene is going to be removed and it's going to come down from the bottom. The purified benzene is going to be combined with the propylene feed, and that's going to be fed into the alkylation reactor. After the alkylation reaction, we have obtained our cumene, but it needs to be purified. So this separator here, it's going to separate the propane and some light components from our stream. It is then going to be fed into this benzene and cumene separator, where the top, that's the benzene, it's either going to go into the transalkylation reactor to produce more cumene, or it's going to be purged out, or it's going to be recycled back and fed into the first alkylation unit. Coming down from the bottom is the cumene stream. It's going to go through this cumene purification 1 separator, and it's going to separate cumene from DIPB. This separator here separates the DIPB from the heavies, where the DIPB is going to be fed into the transalkylation reactor, and the top stream coming out here, the cumene, it's going to go through this cumene purification 2 separator, where the cumene stream down here at the bottom is going to give us our desired 99.98% purity.
The final plant design that Tino just introduced to you meets all but one hard spec, and the soft specs that were missed are not economically viable to hit. And right now we'll take a minute to go through all of the specs that we found were important to bring up. So the first one was the cumene purity, and we passed this spec. The spec was 99.9% pure, and we hit 99.911. The next spec was plant capacity. The capacity was 44,523, and our plant was producing 44,563 pounds per hour of product. The alkylation reactor feed purity was another spec that was hit. All of the components entering the alkylation reactor were of the right purity. And the same goes for the transalkylation reactor. The next spec that we passed was the process max temperature, and this required that no part of the plant to exceed 470 degrees Fahrenheit. The transalkylation conversion was another spec that we hit with 50% and 10%, which we hit dead on. The soft specs that we failed to hit were benzene utilization. We were expected to use 96% of our benzene, where we only used 69.17%. Propylene utilization, the spec was 96%, but we hit 91.8%. DIPB recovery, we were expected to recover 95%, but actually recovered 77.2%. And then cumene recovery. The spec requested for 99.5% recovery, and we actually recovered 97%. We would be required to have more trays or possibly more distillation columns to achieve these utilization and recovery rates, so they were not economically viable to hit, so we proceeded forward with the design. The one hard spec that we were not able to hit was the alkylation reactor selectivity and conversion. Our propylene had a 100% conversion in the reactor, and this could be partially due to the fact that it was the limiting reagent. So I will now take some time to go over the capital estimates, some of the capital costs that are required for this plant. So the total capital cost was $119 million US, and half of that cost came from the IBL construction. 12% came from the OBL, and 15% came from other. The other is the team's cost, catalyst cost, and pre-operational costs, along with a few other costs. The most expensive unit in the IBL was Unit 002, which is the alkylation reactor, and it cost us $29 million to use. The next highest was then 004, the 004 unit, which is the first cumene benzene purification tower. So possible ways for us to reduce our total cost is to take a look at the S0050022 separate tank, and this tank costs $8.6 million and is used to store our final cumene product. And one way we could reduce this tank is to reduce the size. And to reduce the size, we could have a contract where the customer pick up the product more often than they currently are. Currently, we need to store for 14 days of product. Another tank that we could reduce in cost was the S00310 tank. This tank was $8.8 million to build, and it contains propane, hydrogen, and butane vapors. And one way to reduce this tank cost would be to cool the vapors to a liquid, so the tank was smaller. However, this would then have higher costs of refrigeration. And another option would be to avoid using the tank altogether and send the liquid straight to a flare or fuel system.
So now we're going to talk about the economic analysis that we performed. So after developing our design for the plant, we carried out an economic evaluation to analyze its feasibility and identify any potential concerns or any opportunities for improvement. After our analysis, we determined that the base case was not a profitable design. When we analyzed the base case, we assumed the selling price was 42 cents per pound for the cumene selling price. And as you can see on the plot here, at this price, there was no profitable year that increased the worth of the plant. This is indicated by the annual present worth, represented by the blue line on the graph, which was never positive in the assumed 19-year lifetime of the plant, all the way from construction to shutdown. The accumulation of all those negative annual PWs resulted in a very negative end-of-life cumulative present worth, which came out to negative $457 million. Since a discount rate of 12% was assumed, this value is considered to be the NPV 12 of the base case, and because no profit was made, there was a negative rate of return. There was a lot of sources of costs that contributed to the present worth of the plant being negative, but the two largest costs were the cost of raw materials and the cost of waste disposal, in that order. Because the composition of the waste would likely not allow it to be used for fuel, all of the waste produced in the base would need to be disposed of, which led to a cost of 23.65 cents per pound of cumene produced. This took up 35.7% of the total ongoing costs. On the other hand, the raw materials, which were the single biggest cost, took up 59.7% of the total ongoing costs, and the raw materials were projected to cost around 59.7% of those costs. Labor, which is a fixed cost, didn't require anywhere near the amount of spending that raw materials or waste disposal did. It costed just over half a cent per pound of cumene sold, and it accounted for less than 1% of the ongoing costs. In the red are the costs associated with selling, general, and administrative expenses. These were another fixed cost that we assumed would be 4% of the cumene selling price. This cost came out to 1.68 cents per pound of cumene produced, which would be 2.5% of the total ongoing costs. Since no profit was projected to be made in our evaluation model, there would be no income tax. The tax that's represented in green in the pie graph is the property tax, which was a fixed cost based on the capacity of the plant. And the 0.79 cents per pound of cumene that it would require only accounted for 1.2% of the total ongoing costs. The last category was the utilities, shown in the very small sliver of gray in the pie graph. According to our calculation, this would cost 0.02 cents per pound of cumene produced, which would be less than 1% of the ongoing costs. However, there was a mistake in the initial calculation of this cost. The prices that were used for the utilities were too low, which resulted in an underestimation. So after increasing the utility prices in the model to what they should have been, the utility prices increased substantially, as you can see here. The utility prices increased to 3.1% of the total ongoing costs, which was around 2.13 cents per pound of cumene produced. A couple of other fixed costs that weren't included in the ongoing costs are the overhead of the plant, repair and maintenance, and insurance costs. And these were also contributing to the annual deficits that were seen in the annual present worth every year. The total fixed costs, including those that were in the pie chart, came out to 2.77 cents per pound of cumene sold.
We can see that it is not economically desirable to proceed with the base case, and the team decided to do a sensitivity analysis as a way to explore other potential opportunities in making this plant economically feasible. So we decided to do a time-related sensitivity analysis and proposed to reduce the time to build the plant, going from 3 years to 2 years. For the base case, the capital spending distribution was 15, 45, 40% over the 3-year period. After reducing the time to build a plant to 2 years and changing the capital spending to a 50-50 distribution, we saw a decrease in the 19-year cumulative present worth, going from negative 457 million for the base case to negative 507 million. This is due to the fact that more was lost in each operating year than in each capital spending year. What if we reduce the time to reach full capacity, going from 3 years to 2 years? By changing the base case operating capacity from 45, 80, and 100% to 60 and 100%, we saw an increase in the cumulative present worth to negative 454 million. However, the annual present worth values were still negative, and ATROR could not be calculated. The team also explored a cost-related sensitivity analysis by proposing to use the waste products for fuel credit instead of discarding it as waste, as it was done for the base case. An assumption was also made that all waste was used for fuel credit, and this could be used in the cumene production process or other processes. By performing this sensitivity analysis, the 19-year cumulative present worth was calculated to be 837 million, with an ATROR of about 75.42%. Using the waste product as a fuel credit would have the biggest impact on the profitability of the plant, but the assumption of the waste product meeting fuel composition requirements is unrealistic based on the composition reported on the mass balance. So what we considered increasing the selling price of the cumene product. By increasing the cumene selling price to 73 cents per pound, an ATROR of 16.8% could be achieved, and the 19-year cumulative present worth was also calculated to be 21.2 million. But the likelihood of cumene staying at a selling price of 73 cents per pound is unlikely to happen.
As Audrey and Roman previously discussed in the economic and sensitivity analyses, construction of the cumene production plant as it's currently designed would not financially benefit Nitline Chemical. The average present worth over the course of 19 years was calculated to be negative $24.1 million, with the cumulative present worth being negative $457 million over this 19-year period. This indicates that the facility produces a product that is worth less than the inputs and operating costs of the facility. It can be seen that the average operating costs of the facility are higher than the annual cumene sales when operating at capacity each year. This is the most straightforward determination that the process as is not financially reasonable for Nitline Chemical. As previously mentioned, a sensitivity analysis was performed that determined the plant would have positive present worth if the price of cumene were to increase to 73 cents per pound. From this information, the price of cumene should be monitored regularly as it will increase with inflation. The current process design could be viable if the cumene prices reach this point without proportional inflation of capital and operating costs. These costs would obviously need to be reevaluated if the price of cumene reached this point. Finally, the process has higher operating costs compared to the profit obtained from the cumene product. The facility should investigate the costs associated with refining waste streams so that they could be made into a usable fuel for the process or other processes within the plant or the OBL. This would reduce the costs associated with waste disposal, which are significant. Additionally, this option would make the process more sustainable. This should only be pursued if the capital and operating costs of the fuel waste system are less than that of the current waste removal system. Furthermore, the design team should look into the economic implications of sending vapors to flares as opposed to the somewhat expensive process of storing them in tanks, which is currently in place. This would reduce the capital cost of the system, specifically in stage 3, which is the removal of lights and propanes from the process. Finally, the design team should explore the possibility of removing cyclohexane and N-hexane in the process to decrease the alkylation reactor size. Decreasing the size would decrease the capital costs of the reactor, as well as the operating costs by reducing the utility and catalyst requirements. Cyclohexane removal is difficult due to the similarities in boiling points with benzene, but using liquid-liquid extraction as a separation technique could be an efficient method of removing cyclohexane from the process. This extraction column would need to be strategically placed in a stream with a higher cyclohexane concentration. So this concludes our design and recommendations for Nitline Chemical's Gulf Coast facility. Thank you for your time, and we look forward to hearing your feedback.